Good evening, everyone. I'm Jyoti Sharma, and this is last week that we will do some revision for the course Environmental Quality Monitoring and Analysis. So this live session will be from 6 to 8, and here is my brief introduction. That right now I'm a PhD student from Mysore, Bhopal, and I did my master's from FRI Dehradun, and my undergraduate was from University of Delhi. I have cleared UGC NET GRF and ICR NET also. And right now I'm a PMRF research fellow. So that's how I have the responsibility to take this live session. I already have experience, NPTEL experience to teach. So I already have taken the courses Air Pollution and Control, Environmental Chemistry and Microbiology, Basic Environment Engineering and Pollution Abatement. So that's how I do have experience of taking such kind of NPTEL courses. This is how we will proceed, as this is the last class, but I just want to tell you again that I will have a lot of MCQ questions. So today, the MCQ question will be related to all the weeks, and I have mixed some MCQs together. So we will have MCQ question. Each will have 4 options, and you people are encouraged to write in the chat box which one you're thinking is the right one answer. So your participation is highly valued for this. Okay, so as I told you, this is kind of a revision class because this is the extra class that I'm taking right now. So in for each week, I will have few MCQ question, and then we will go from week 1 to week 8 or 9, because from week 9 we are having the same type of question. So and we already have covered that a lot. So what plan we have right now is that we will go from week 1 to week 8, and then I will be taking MCQ question in each week. And yeah, you are encouraged to write in the chat box which one is the right, because I will explain you also why that option is right and which option is not suitable. Okay, so we are starting with the revision for the week 1, where we just introduced the course. This was related to the chemical of concern, and most of the time we sticked on some particular chemical A. And then water quality and screening parameter. So for example, it is a TDS, turbidity, color, taste. So we will talk about these questions also, why this is the case, why we have why we can smell the water, or why there is a color in the water, what are different chemicals that we have in the water, so to check the water quality. For air quality parameters, we have particulate matter, so we also have some question on that. And yeah, so let's start with first MCQ question from first week. Okay, so the first question is, from an environmental risk perspective, contaminants are more likely to persist for longer duration in, and I have 4 options here: Lotic system due to turbulence, Lotic system due to dilution, lentic system due to low flow and sedimentation, both system equally. So this is something like that. If we have, let's say, a chemical A, and this chemical A, we have, let's say, some water body. For example, we have river, right? But this river body can be anything else. For example, it is a pond. So our contaminant A may be present in the river, or let's say maybe present in the pond. So the question is, what kind of water bodies will help to persist this? Sorry, this is again chemical species A. So which water body will help this chemical species A to persist there? Is it river or not? Is it pond that will help to persist it more. uh, and based on that only, you have two type of system. So we have lotic system. So these are water bodies. So water bodies can be of two type. The first is lotic, it can be lotic, and second is it can be lentic, right? So lotic means flowing. So whenever we do have flowing water, that will be considered under the lotic system. If we do not have the flowing water, so it means we have still water in that water bodies, then it will be known as the lentic water body, or lentic type of water body. So what do you think, what kind of water body will help you to persist that chemical species A be there, or which will help it to dilute, or which will help it to move from one place to the another place, or it can spread, it can diffuse, it can move from one place to another place. So okay, so if we are talking about the lotic system, which means it is the flowing water, and the example of this flowing water is the river body, right? For the lentic water, this may be pond. So river will help us because river have some flow, right? River have some flow rate. That flow rate will help this pollutant A to move from one place to the another place. So that's how it will help us to move from one place to another. So what I'm trying to say is that river is the one kind of water body that will not help to persist it at the for the longer duration, because it help for the dispersion. But if I'm talking about the pond, then pond will help to persist because it doesn't have the flow rate. So based on that, I stick to the answer C, that is the lentic water, due to low flow and sedimentation. And why this sedimentation? Because if we will have low flow, it means your pollutant can sediment at the base also. But if it is a river, then because we will have the advection flow or bulk flow, so your pollutant will move in the horizontal direction, right? So that's why contaminant will persist more in lentic system. An example of lentic system is pond. So the answer will be C. If you can see here the sediment. Okay. So the next question is, because we are revising our week 1 to week 8 content. So that's why I have multiple questions related to week 1 to 8. So we are moving, we are having the revision today. So this question is related to the soil component, which is rich in oxide of aluminium, iron, magnesium, calcium, contributing strongly to adsorption processes. And we have four options here: sand, silt, clay, bedrock. Which type of soil is rich in oxides of aluminium, iron, magnesium, and calcium, and that will help us to adsorb? So the hint is, um, if you are if you are interested for the pottery, or to create the pots, and for anything, or for example chulha, if you want to create, then what kind of soil we use? Because uh, as the question is, we have a soil in which we have oxide of these, and because these are mostly cations, positively charged, right? So this positive charge cation will attract with the anions, and then how that's how that kind of soil help to absorb that. Another example that I can give you is that whenever we are having the sanitary landfills, so at the base we use a particular type of soil in such a way that can absorb the leachate, and so that this leachate is not going up to the groundwater, right? So such kind of soil is, yes, it is clay soil. Clay soil have aluminium, have a lot of type of oxides of different metals or alkaline, for example aluminium, magnesium, iron, and the calcium. So I just show you the structure. So the one type of clay, so we do have different type of clay, right? And thousands of different clay structure we have. So one of the clay that we have is the kaolin. This is kaolin. So the one type of clay is kaolin, and in which, if you are seeing, that we do have oxides, hydroxide, aluminium, silicon, and they are having the weak bond, and that's how such kind of interaction among the cation and anion will help with the adsorption, and that's how it can help us to prevent the leachate in the groundwater if we are having the layer at the bottom in the landfill sanitary. Okay. The next question is, because right now we are talking about chemical of concern, so we must know different type of chemical and what are the properties for these particular type of chemicals. So the question is, which heavy metal is correctly matched with its toxic ion form frequently encountered in environmental contamination? Sodium, mercury, potassium, calcium. Yeah. So the answer will be mercury. Mercury is the heavy metal. Actually, sodium, potassium, and calcium are not the heavy metal. So, for the definition of heavy metal, do you know what is the definition of heavy metal? How we can consider which one is the heavy metal and which one is not? Uh, Mostly, it is based on the specific gravity. So, whenever we have specific gravity more than 4 to 4.5, if specific gravity is more than this 4 or 4.5, then we are considering those atoms as heavy metals, or those metals as a heavy metal, and among which the one is mercury. And yeah, and the important thing is, mercury may have different ionic form. For example, mercury have the oxidation state 0, mercury have the oxidation state 1 plus or 2 plus, and so on. Okay, so but the important point is, some of the ionic form may be dangerous and some of the ionic form may be normal for us. Okay, so this is mercury oxidation state 2, which is important for us because this is creating the health risk. Along with mercury, we may have different heavy metals. For example, can you give me the example for some heavy metals? Antimony, lead. What more heavy metal we may have? Chromium. Okay. So we may have different heavy metals, and these heavy metals are mostly creating the risk for the human. So yeah, answer is B. And I'm giving here some of the heavy metals. So for example, we have lead, we have mercury, we have arsenic, we have cadmium, we may have fluoride. I'm not sure whether fluoride is the heavy metal or not, but these are the chemical of concern. And if we are exceeding some concentration, some threshold, then we may have the dangerous impact on human body. And the important thing is we also need to know the source for these chemical of concern. For example, if it is the lead, from where we can get the lead? So we can get the lead from paint, from battery, from old pipe, and so on. For the mercury we can find from the mining place. From even iron mining also can create some mercury. Arsenic is mostly geological. We can get it from geological formation. So mostly it will get we will get it from groundwater, and this is the case of Bangladesh and West Bengal, where we can have a lot of arsenic in the groundwater. Then we have cadmium and the fluoride. So fluoride we can have in the um, northwest part of India. So for example, Rajasthan or Haryana, we can have the high concentration of fluoride. Okay, the next question is about the bioconcentration factor. So how we can calculate the bioconcentration factor? We have four options: dividing the chemical mass by the organism body weight, concentration of chemical in organism divide by concentration of chemical in environment, concentration of water divide by concentration of chemical in organism, total biomass of organism multiplied by chemical volume in environment. So yeah, from name only you can from name only you can see. So if this is the bio concentration, so there is a concentration of, let's say, chemical A in bio means organism, in organism, right? So the concentration of A in organism, but because if it is a factor, then yeah, we have to divide it with something. So the concentration of this chemical A in environment. So there are some cases where in environment the concentration is low, but in organism the concentration of that contaminant A may be higher. Can you give me example of some of these chemicals where bio concentration may be more than one? Bio concentration more than one, it means the concentration in organism is more than the concentration in environment. Can you name some chemical of which BCF is more than one? So the very common example is DDT. Very common example is DDT, where DDT concentration in environment may be lower, but in organism it will be higher, because this is hydrophobic in nature, and it is loving the the bio concentration of so yeah, I just want to tell you that we do have three type of pesticide. The one is chlorine based, second is phosphate based, and the third is carbamate. So, the bioconcentration factor of this chlorine based pesticide is always greater than this phosphate based and the carbamate based, because it can persist more, and that's how the tissue or the fat tissue of organism can take it, can increase the concentration in the body, and that's how these chlorine based pesticide are more harmful as comparison to the phosphate and the carbamate. So yeah, this is B, that this is the concentration of chemical in organism divided by the concentration of chemical in environment. We already have talked about this, then I'm just skipping it. Okay. Which of the following contribution mainly to the total dissolved solid in water? Because right now we are talking about the water quality and the screening parameters. So one of the screening parameter is to check the TDS of the water. So the question is, which type of chemical or which type of particle is contributing to the total dissolved solids in water? So I have four options here: sand and silt, microorganism, inorganic salts and ions, or the clay particles. Okay, so yeah, the answer is C, that is inorganic salts and ions. So if we are talking about this salt and silt, these are not contributing to total dissolved, but these are contributing to the suspended solid. Microorganism will also help with the suspended solids, total suspended solids, so you can say TSS also. But this inorganic salt and ions, because these are hydrophilic, these inorganic salt and ions have the anions and cations. These anion and cations uh, can make the bond with the water, right? Because we have the anion, we have cation, and that's how there will be bond of this hydrophilic inorganic salt and ion with the water, and that's how it will be dissolved. So yeah, inorganic salts and ion is contributing to the total dissolved solid. If we are talking about the clay particle, then what will happen with the clay particle? Some of the, so yeah, clay particle have, we talked about this, right? Clay particle may have some metals or some cations, but will also have some part of this sand and silt, right? So clay particle will change the color of your water, because it will get dissolved also, but along with the dissolve, yeah, so it will also dissolve, and yeah, there will be suspended part of clay we will have in the water. So this clay is not just giving you the TDS, but it is also giving us the TSS. So the right answer will be the inorganic salt and ions. Yeah. Okay. So which water quality characteristic is most strongly influenced by hydrophilic inorganic ion rather than organic compound? Odor, taste, turbidity, or color? So for example, we have water, and we are adding in one, we are adding inorganic, and another one we are adding organic compounds. So if we are adding inorganic compounds, so what quality characteristic it will provide us? Will it change the odor, or will it change the taste? Will it change the turbidity, or will contribute to the turbidity, or it will it change the color of your water? If we are adding hydrophilic, means water loving inorganic ions rather than organic compounds. Let me give you the hint. Because we have four option, and we need to cancel some of the option. This order, if we are talking about this order is mostly due to the volatile compounds, right? This is, and volatile, mostly volatile organic compound. So this should not be the answer because we are talking about the inorganic ion. Then in last question only, we discussed that inorganic ions is giving us no inorganic ions are giving us TDS, but not TSS. Inorganic ions are giving us the dissolved solid but not the suspended solid. And if you remember, turbidity is due to total suspended solid. So this is also not the right answer. Turbidity is mostly due to suspended solid, because there will be some reflection and all, and that's how this will give us the turbidity, right? And this turbidity is not by inorganic. Now we have taste and color. So yeah, so we have taste and color, and in which only we will have the answer, and the answer is taste. Okay, let me tell you why this is taste and it is not color. I think I have yeah. So the color is due to your dissolved substance, because it will completely bind to each other, and yeah, it will be dissolved completely. So this is giving the color. For example, uh, you already have drink ruauza, right? So this ruauza is nothing but it is that we are dissolving something in the water, and that is giving us the color, right? So this is the dissolved substance. If it is a turbidity, then we already have talked about this is the suspended solid. If it is a taste, then taste is due to dissolve inorganic ions. So yeah, uh, this question may have both the color and taste. And if we are talking about inorganic, so most of the time, so just see that water, if we are talking about the water, this is non-polar sorry, this is polar in nature. And inorganic compound also polar in nature, and that's how there will be the interaction between this inorganic. And we will have rarely any organic substance that will dissolve. Obviously we will have few exception, but most of the time this is inorganic ions that will be dissolved. So the taste and the color is given by the dissolved substance only, but if it is a dissolved inorganic, that will give us the taste. And odor, this will be given by the VOC. So I think that slide is making things much clear. Okay, because we are talking about the water quality parameters. So one of the way to check the quality of water is to check how much oxygen demand we have in the water body. So we have three parameters by which we can calculate the oxygen demand. Okay, the first is theoretical oxygen demand, the second is chemical oxygen demand, and third is biological oxygen demand. And you have to tell me the relationship among these three type of parameters. Which one is greater than which one? If we have theoretical oxygen demand, chemical oxygen demand, BOD, that is biological oxygen demand, which one will have the highest value? So for example, in the water we have glucose, right? And glucose need to be broken down, adding some oxygen, and that will change this glucose in CO2 plus H2O, right? So how much oxygen do we need? This is your oxygen demand. How much oxygen we do we need is your oxygen demand. But we do have three type of oxygen demand: theoretical, chemical, and biological. So uh, actually the C will be right answer, that theoretical oxygen demand is higher than the chemical oxygen demand and then the BOD. So let me tell you why. So I gave you the example of the glucose, right? If this glucose is broken down by the organism and is giving you the CO2 and H2O, this will be the BOD, right? So the oxygen demand by the organism to break down the any chemical, right? So this is your BOD. Then if we are talking about the COD, then what we are doing, we are just adding some strong oxidizing agent, so that this glucose can be broken down and can give us the CO2 and H2O. So what, so why COD will be better, will be more than BOD? Because organism may or may not break down some hard substance, but strong oxidizing agent can break down those non biodegradable substance also. So for example, I'm giving you the, so in place of this glucose, if we have lignin, right? Organism can barely degrade this, or can barely convert it into to CO2 and H2O, but strong oxidizing agent can uh, oxidize it, so it will take more oxygen. So yeah, BOD and COD, so COD will always be better, more than BOD. Now coming to the theoretical oxygen demand. So what is the theoretical oxygen demand? So it is irrespective of either it is biodegradable or degradable. The only important thing is what is the chemical formula of that particular substance that we need to degrade, right? So for example, if this is a C6H12O6, then based on this chemical formula we will add O2, and then we will have some stoichiometric calculation how much molecule of this oxygen we need based on this chemical formula of your interest, chemical of interest. And that's how it will be even more than your COD. Okay, so the answer should be theoretical oxygen demand is more than COD, and COD is more than BOD. So C answer is the right one. Okay, now we are moving little bit about the air quality parameter and what we are interested into. So this is something that you have particles in the air, right? Particles in the air, and based on the size of the particle, it can settle down in some time, right? So we are interested into settling velocity. So for example, we have dust, and we have very fine particle, let's say particulate matter 2.5, and dust may have the size of particulate matter 10. Which one will settle down easy? This one, right? This one will settle down easy as comparison to the particulate matter that have the size 2.5. So if we want to calculate this settling velocity, we do have a particular formula for that, which you have to tell. Okay, so this formula, the settling velocity, the velocity at which it will settle down, the particle will settle down, this formula is given by the Stokes law. Okay, and so what is that formula? This question is related to that only. So according to Stokes law, the settling velocity of small spherical particle in a fluid under laminar flow condition is directly proportional to the square of the particle diameter and density difference between particle and fluid, the particle's surface area only, the viscosity of fluid, the inverse of gravitational acceleration. So yeah, A answer is the right one, because if we want to calculate the settling velocity, so this is equal to d square rho g divide by 18 mu. And here, this one, this rho is uh, this is your density difference between your particle minus density difference of your fluid, or you can say fluid can be air, right? So, and because most of the time the density of this we consider one, so we most of the time remove this. So the settling velocity is directly proportional to the square of your particle diameter, that is d square, multiplied by the density, and here you can say the density difference between particle and fluid, multiplied by uh, gravitational acceleration. So this is inverse, so this is not the right one, right? Divide by 18, and mu is viscosity. This is viscosity, and viscosity of the fluid should be inversely, not directly. So this is also not the right answer. Surface area is not important for us. So yeah, right answer will be A. So whenever we want to calculate the settling velocity, we can calculate it using the Stokes law, and Stokes law says that settling velocity is equal to d square rho z divided by 18 mu. And because this is square of the particle diameter, that's why the dust particle will settle down easily as comparison to the very fine particle. So yeah, I already have explained this. Okay. Next, what we are talking about is some of the instruments we need. For example, we are having air purifier, right? We may have air purifier, or another example that I can give you is, let's say chimney is releasing a lot of particles and a lot of chemical or gas, but so we ensure that there should be pure air or pure gas, or not dangerous gas. So here, somewhere here, before, or let's say here, we are some installing some instrument, right, based on which the particle will be taken up by that particular uh, technique or instrument, so that it doesn't go to the air. Okay, so in that particular instrument, there is a different principles that we are focusing on. And this principle may be so the example that I'm giving you, air purifier, for example, if we have air purifier, okay, so in air purifier, there must be some principle by which we are resisting air to go to any other place. We are taking that particular particular particulate matter into that air purifier only. So this is based on a lot of principle, and these principle may be based on different mechanism, and these mechanisms are Brownian diffusion, inertial impaction, interception, gravitational settling, and electrostatic deposition. So you have to tell me which particle size different mechanism can take different size of particle size, or you can say the deposition. So important thing is here the deposition. A different mechanism will deposit different size of particle, and based on that we design our instrument to deposit the air particle. So let me give you some hint. uh, let's say if you have particle size more than 10 micrometer, it means it already its settling velocity is higher, right? Settling velocity of the particulate matter that have more than 10 micrometer, the settling velocity is already higher, so it will settle down easily. So what we just need is gravitational settling. Under the influence of gravity, it will settle down. But if we will have particle size smaller than these, then gravitational settling will not help us. The particle will be in air and will take a longer time to settle down. So what you can see is that this is the right match. Then the another thing is uh, this Brownian diffusion. Brownian diffusion is associated with very fine particle, because that's how there will be the zigzag motion. And because of that zigzag motion, a particle may collide to your instrument plate or something, and that's how it can deposit. So Brownian diffusion is related to very fine particle. So this is your D will be related to 1. Then what else? We have now inertial impaction, interception, and electrostatic deposition. Electrostatic deposition is more stronger than inertial impaction and interception. So what should be the answer? So B is the right answer. So what it is saying that, okay, I have given the wrong thing, I think. Whenever we have, let me check this. Yeah. Oh, okay, it is right. So this is something that if we will have more than 10 micrometer, then what we can use is we can use inertial impaction, and we can also use gravitational settling. If we have this B1, B1 have this third one, interception. C1 have the fifth, electrostatic. As I told you, electrostatic is for very finer particulate matter, but um, diffusion is finest one. So that's how what you can say is the diffusion is the first for very fine particle, followed by electrostatic deposition, then your interception and impaction, and then you will have the gravitational settling. And that's how you can give the answer. So I have one figure I think that can explain. So if you have diffusion, so diffusion is something whenever you have uh, particle because of your chemical potential, we already have learnt about this, right? If there is a difference in the chemical potential, it will move to some place. So this is diffusion. Interception is when your particle is flowing in the air with some direction, but this part will collide with your fiber, right? So for example, we are wearing the mask, right? Mask can trap some of your particulate matter. The mechanism, what mechanism that mask is following, the one mechanism may be interception, right? So what it is, that your fiber may interact with your particulate matter, and that's how this will be deposited in the mask and will not go to your nostril. This one is the first. Then inertial impaction. Whenever your particle size is larger, then even if air is following this path, due to inertia, due to momentum, it will go in this direction only, and it will directly strike to your fiber, and that's how your particle will be taken up by the fiber. So this is your inertial. And electrostatic is, we will create, artificially we can create positive and negative charge to the particulate matter, so that it can attract to the positive charge, and that's how it can settle down. So we have different filtration or deposition mechanism that we can follow in different instruments. Yeah, we already have discussed about this, so yeah. So we talked about our chemical of concern, we talked about the water quality parameter, and we talked about air quality parameters. Now we are moving to a very important week, that is the week 2, which is physical and chemical property of interest, partition constant. This is very important because till week 12 we were talking about this partition coefficient, so your base must be very clear for this partition coefficient. And in one partition constant is soil air partition constant, we will talk. So we will have 5 or 6 questions related to, I think, this week too. Let's solve this. Which parameter and unit best describe the equilibrium partitioning of a pollutant between air and water? And you have 4 options here: solubility, vapor pressure, Henry law constant, diffusion coefficient. Equilibrium partitioning of the pollutant between air and water. So for example, I'm giving you the example of, let's say, oxygen. So oxygen is having the equilibrium in atmosphere and in ocean, right? Some of the oxygen we have in atmosphere, and some of the oxygen, let's say, we have in ocean, and these oxygen molecules are in equilibrium. If equilibrium is not established, then what will happen? They will try to balance, they will try to maintain that equilibrium. So some of the oxygen molecule can go to the atmosphere, and some of the oxygen atoms from the atmosphere can go to the oxygen, based on the equilibrium that we need to maintain. So this is, let's say, our chemical, this oxygen is our chemical A. So this is something that the concentration of your chemical A in air, and concentration of your chemical A in water. One is for air and two is for the water. So we will have some constant. So this constant is what? And this is equilibrium constant, right? So what should be the answer for this? Yeah. So yes, C answer is the right one. So this is the Henry law constant, right? So so Henry law constant define the concentration in air that is directly proportional to the concentration in water. And I give you very current example that, for example, we have we have ocean, right? Ocean have some dissolved oxygen, right? If the temperature of your ocean will increase over the time, that may reduce the solubility of your oxygen in the um, um, oxygen solubility in ocean. So what will happen if dissolubility is reduced because of temperature increment? This oxygen may go out in the atmosphere and may create the equilibrium, right? This is very normal thing. But the important thing is CO2. If temperature increases and if this solubility increases in the ocean, and if this oxygen will go in the atmosphere, then CO2 will increase and global warming may further increase in that case. So this is just the case of the equilibrium, right? If the temperature will increase in the ocean, CO2 solubility may reduced over the time in ocean, and ocean may release a lot of CO2 in the atmosphere, and that's how global warming may enhance due to the global warming. So this is the example of very nice example of equilibrium partitioning of your chemical of concern. Okay, so because we are talking about partition constant, right? So one partition constant is 32 K star 32, and you need to tell me the unit for this. So what is this K star 32? This equilibrium or partition constant, this star is giving you the equilibrium condition, and this is K is your partition constant, and this is something, the concentration of your chemical A. 3 means solid, right? 2 means water. So solid may be your soil. So the concentration of A in soil divide by concentration of A in water. So let's say I'm giving the example of benzene. Benzene may be present in soil and may also be present in the water. But this partition constant will determine where your benzene will be more, either in soil or in water. Right, based on the value, you can tell, okay, the tendency of this benzene is higher, let's say in soil or in water, based on whatever value you have for this partition constant. Now you have to tell me the unit. So you have to first see the unit for this and the unit for this one. So what is the unit for concentration of A in soil? Concentration means mass upon volume, right? Mass upon volume. But here, if we do have soil, then in place of volume, we are considering the mass only. So this is mass by mass we can take. So this is something that this is the concentration. So let's say we have kg of A divide by, let's say, kg of soil. Okay, then we need to divide by this concentration of A in water, right? So this will be mass by volume. Water we can consider into the volume. So the mass of A will be your kg, because this is in denominator. That's how I'm just reversing it. So this is your kg, and the volume of water will be your liter. Is it? Cancel, cancel. What will be remaining? This is liter per kg. Yeah. So C answer is the right one. So this is liter per kg. How we are considering? We know that if this is 3 2 means concentration of A in soil divided by concentration of A in water. Concentration is mass by volume, but if this is the case of soil, then we can have mass by mass, and if it is water, then this will be mass by volume. So kg per liter, we are dividing it, and that's how what we are getting is liter per kg. So C answer is the right one. Okay. So if we do have large value of K star A32, indicate that pollutant A is highly mobile in groundwater, preferentially partitions into pore water, strongly sorbed to soil sediment solid, rapidly volatile to air. So the last question only. So we talked about this K star 32, and this is concentration of your chemical A in soil divide by concentration of this A in water, right? Because this is 3 and this is 2. So if we do have large value of this K, large value means if this K is more than 1, more than 1 means this value is higher, right? That's why this is more than 1. So this, if this value is higher, then what we can say is concentration of A is higher in soil as comparison to water. Why we can say this? Because the soil absorption capacity of that particular chemical A is larger as comparison to the water, right? And that's why what we can say is it can strongly absorb to soil sediment solid. So let me give you again the example of benzene. Benzene is organic in nature, right? Benzene is organic in nature. Water is not liking the organic part, right? So benzene, but soil may have clay particle, right? Soil may have cations and anions, as we already have talked about. So this benzene will make more bond formation with the soil as comparison to the water, right? That's why the concentration of your benzene will be more in soil as comparison to the water, and your partition constant will have more value, more than 1, right? So this is how we can decide which particular chemical have that particular tendency. We can talk about this based on your partition constant, based on the value of your partition constant. So that's why C is the right answer. Okay, now the question is on dissolved oxygen. So we have river. Let's say this is river that was following. That river have the flow rate of 30 meter cube, right? And that river have dissolved oxygen of 8 mg per liter. Then it is receiving the wastewater discharge. So we are adding wastewater into it, and this wastewater have flow rate of 5 meter cube per second, and dissolved oxygen is just 2, because here oxygen demand is higher. That's why dissolved oxygen is 2 as comparison to 8. Then if we are mixing it, then we will have some dissolved oxygen resultant of this river and this your drainage part. So can you calculate the mix dissolved oxygen that we will have after we are adding that drain into a river? River and drainage both have different dissolved oxygen. So how we can combine and how we can tell the mixed dissolved oxygen concentration? So let's say this is C1 and this is Q1. This is, let's say, C2 and this is Q2. And we need to calculate CW and QW. So this is something, your CW will be equal to C1 Q1 plus C2 Q2 divide by Q1 plus Q2. This is how you can calculate. So this will be 30 multiplied by 8 plus 5 multiplied by 2 divide by 8 plus 13. So this is how you can calculate the mixed dissolved oxygen concentration. Yeah. So B answer will be the right one. So yeah, this is how you can calculate. Okay, the another partition coefficient that we can have is K or W, that is best described as ratio of concentration in air to water, soil to water, octanol to water, ratio of vapor pressure to solubility. We have another partition constant, or you can say coefficient, that is KOW. And what is that KOW? What is the ratio? Ratio between air to water, ratio between soil to water, ratio between octanol to water, or ratio between vapor pressure to solubility. Yeah, from question itself, you can tell if this is octanol water partition coefficient, then there should be, so this is something, the concentration of octanol. So concentration of A in octanol divide by concentration of A in water. But why it is important for us? Why we are just taking one chemical, that is octanol? Why we are not replacing it with a benzene, or not changing or replacing it with oxygen or CO2? Why octanol only? Why we are interested in octanol water partition constant, not any another constant? Because this octanol has a very similar properties like the tissues that we have in the body, human body or microorganism body, right? So based on that, we can estimate one chemical. Let's say if it is a benzene, so benzene will be more in, the tendency of benzene is more be in human body or more be in the water body. So this is how we can calculate. And most of the medicine or pharmaceutical industries are depend on this octanol water partition constant whenever they people are designing any kind of medicine, because we need the medicine and medicine should dissolve in the tissue. Okay, the concentration of that medicine should be more in the tissue rather than in the water. So here partition coefficient should be more than 1. And that's how they people design the medicine solubility, or about the medicine dissolve, whether it will be dissolved in the tissue or not, whether it will be more in it will go more in your tissue or not. So this is very important, because octanol is very similar to whatever we have, the liquid that we have in our tissue. So that's how octanol water partition coefficient is important. Okay. Which soil moisture condition corresponds to less than one monolayer of water coverage on soil particle? Wet soil, damp soil, saturated soil, flooded soil. Less than one monolayer of water coverage on soil particles. So let's say we have soil particle. These are our soil particle. And soil particle may have water coverage. So let's say, let me take the example. So let's say this is our water, and water is covering this soil particle. So this is one monolayer of your water, one monolayer, right? If here we do not have anything, we do not have water coverage, so we can say this is a zero monolayer of your water coverage. And let's say here we have here, here, or let's say here, right? So this will be uh, it is not zero, but it is less than one monolayer. So this is 0 to 1 monolayer of your water. So yeah, so that type of soil will be damp soil, because if we will have one monolayer of water coverage, that will consider into wet. If there is no any monolayer, that will be dry soil. And if we do have less than one monolayer, then this will be your damp soil. And saturated, even in the pore water, so it may be that we have this monolayer, but here we have air. So this is wet. But if this air, it is replacing, if we are replacing this air with the water, then this will be saturated. So saturated, wet, damp, dry, flooded. Flooded is similar to the saturated one, or it can be similar to the wet one based on the condition. Okay. For the wet soil, now we are talking about the wet soil. So this is, let's say, your soil particle. And because it is wet, then we may consider that there is a layer of water around it. So this is your water around it. And what we want is the interaction of your solid air. So we need solid air partition constant coefficient. So we need here. So what we need is the concentration of A in soil divided by concentration of A in air. And this will be K star A31. So how we can express this? So yeah, B answer is the right one. And why B answer is the right one? Because this soil first interact with the water and then it interact with the air. So this must be cancel out, right? The concentration of your A in water. But the thing will be the concentration of A in soil divide by concentration of your A in water, and then water to air. And this air will be cancel out, and this will give you WA3 divided by SA3, SA1. right? But because at the interface we have the water, then we have to consider this also. So that's how B answer is the right one. Okay, so if you have ratio SA2 divided by SA1 in the derivation correspond to organic carbon partitioning, diffusion coefficient, inverse of Henry constant, or the vapor pressure. Yeah. So C answer is the right one, that this is the inverse of Henry constant. Henry constant was your A in air by, so if we are reversing our Henry constant, this is 1 2, if we are reversing our Henry constant, so this will be K21, right? And K21 is the inverse of your Henry constant. Okay. Again, we do have wet soil. The correct expression for soil air partitioning. Again, we are having this K star 31 soil air partitioning. Then what will be the formula for that? KOC, FOC, H, KOC, FOC divide by H by KOC, and H. This is very important formula actually, if you want to calculate the soil air partitioning. Yeah. So B answer is the right one. So this is KOC multiply by FOC and divide by H. So this FOC means what? And this KOC means what? So this KOC means concentration of A that you have in the soil, right? But in the soil, it is in organic carbon. Right. So what you can say is, let's say you have soil particle here and soil particle. This is, let's say, your organic part, organic carbon. Here you have organic carbon, and here also you have organic carbon. And this A is mostly present on organic carbon, right? So what we will do is that you need the concentration of A in organic carbon of your soil. First thing, this is important for us to know. This is first thing. But we also need to know how much organic carbon we have in the soil. So another thing that we need is the fraction of your organic carbon, right? So how much organic carbon you have in the soil. So this will be your FOC, fraction of your organic carbon, right? So this is your FOC. Then you have KOC, uh, and then you have H, that is the Henry constant. So let me show you the derivation part. So yeah, so the first thing that you need to know is we have K star A32, right? So this is your concentration of A in soil divided by concentration of A in water, right? But here what we are interested is, if it is concentration of A in soil, then this is mass, right? We are talking about the mass. And here we have M3, that is yeah, so we have M3. Then what will happen? So here, this is something that we have the mass of A divide by the mass of your organic carbon multiply by mass of your organic carbon divide by the you can say the volume, right? The volume of your soil, m3 you can use here. And so this is your uh, concentration of A in soil, right? This part is this one, and this one is your remaining for this 2. So multiply by the concentration of A in 2, right? So this part, this is the fraction, right? Fraction of organic carbon in your soil, this will be FOC. This will be your FOC, and then the remaining part MA by MOC, and this part, so this part, so we will have this part, right? So this part, what we can see is this one is your concentration of A in organic part. So we are equaling it with WaOC, and we have this remaining rho A2. So we will have this equation and the FOC, and this equation we are knowing as KOC. Okay, so this Ka32 is giving us KOC and FOC, right? And then, yeah, if it is the wet soil and if we want A31, we need row A1 also. So first we will have this 3 1. So we already have, for this one we already have KOC FOC, and for this part we are having the inverse of Henry law, and this is how it will be derived. You can read more about this. Anyway, another is now the important part for the application part is the mass balance. So if we are doing the mass balance and we have K star A12, that is equal to S star A1 divided by S star A2, the correct expression for K star A12 is. So this S is nothing but this is the concentration of A. S is similar to this one. So if you want to do the mass balance, so what will be the value? And this S naught A2 is your initial concentration of A in water. And you need the mass balance. So what expression will give you the right way to solve if we have some mass balance type question? So the C answer will be the right one, and the thing is we have to derive it. Why C1 is the right one? So I just give you the hint, and then you can go for the solution. So this is something that initially, so mass balance is whatever initial mass rate. So the important thing is we are talking about the mass rate, mass by time, right? We are talking about the mass rate. So initial A will be equal to the final A. Okay, and so that's why if we want mass rate, then we have to multiply this density with the volume, right? So here we are having the mass. So mass of A, initially don't go with the mass rate because per second it will be the constant. So now we are focusing on, let's say, mass only. So mass initially whatever we had for the A, if even if it is distributing among two compartment, the mass should be equal. Okay, this is how we are balancing the mass. So what we are saying is let's say we have air and water, we have air and we have water, and in the air we had some mass. And how we can define the mass? So mass will be your density multiplied by your volume. Okay, so this is the mass of A that will have, that we had in water, and mass of A that we had in air. After equilibrium, there will be some change. So for example, we are putting some benzene in the air and we are putting some benzene in the water. Okay, but over the time there will be some equilibrium condition. Some benzene will go to the water side and some benzene will go to the uh, air side, and that's how the equilibrium condition will be there. So the mass will distribute among air and water, right? So here what we are seeing is that initially it was, here we had the node, right? But later on we will have the equilibrium condition, so we will have some mass of A in water in the equilibrium condition, and we may also have mass of our A in air in equilibrium condition, so we have to equal it. Okay, if we are just putting our concentration of A just in water, if we do not have a, if we are not putting our concentration of A in air but just in water, then this value is not important for us, right? So what will be remaining? This one and this two, right? And what we know is K star A12, we have learnt about this, right? Henry constant Ka12, and and we also, then we can calculate this rho A2 and rho A1, and based on this, if we are putting here the values, then we will get this one. Right, so here you can derive such kind of equations based on what kind of problem you have. Just think that you need to keep in mind that you have to balance the mass. Okay, now coming to week 3, I think we are slower, but yeah. Um, Detection of the same pollutant fingerprint in river water, groundwater, and a nearby industrial discharge most strongly spot liability establishment for the pollution source, diffuse non-point source pollution, natural background contamination, sampling bias due to seasonal effects. Because we want to now model our water contaminant and air contaminant, then we need to know some pollutants and how we can identify that pollutant. So if we have same pollutant fingerprint in river water, groundwater, and nearby industrial discharge, that will spot what? So let's say if there is an industry and the industry is giving you some chemical A, right? So this is and this chemical A is, we can find this chemical A in the river, we can find this chemical A in the groundwater, and even in the industrial discharge, and this industry is also giving us some chemical A. So this will strongly spot liability establishment for the pollution source. So I'm not talking about just the chemical. So chemical A will have some property that will not change, that we will find everywhere. So let's say this chemical A may not just be just one molecule or one compound, it may be anything, right? So let's say I'm saying the example of isotope. If we have some particular isotope that is released by our industry, and that particular isotope you are finding in the river, you are finding in the groundwater, so you can say, okay, that industry is giving that particular chemical because that chemical have that particular isotope, and that particular isotope we can found in the groundwater and discharge. And that's how the case that we can win related to the environmental concern, right? So this is the, that particular industry have to pay a penalty and we have to pay, it has to pay a fine, because it is the fingerprint. So this is kind of fingerprint that we can find that have alignment with the industrial discharge, with the with that particular fingerprint we can find in the river water and the groundwater. So this is how there may be some case, and we may that industry will have some liability things, right? So A is the right answer. So fingerprint is not just same pollutant, but same compound mix, maybe same ratio, maybe some same degradation pattern. So this will create a fingerprint, right? Okay, which technique is most appropriate for analyzing trace organic pollutant? For example, pesticide in water, flame photometry, gravimetric analysis, pH meter, GCMS after extraction. So if we want to analyze some trace organic pollutant, for example, pesticide, then which technique is most appropriate for it? So the technique for this is, because this is organic, right? This is organic, then we are not going with the gravimetric, because for the gravimetric the concentration should be very high, but this is trace. So this is not the right answer. pH, pH is for the pH meter, for the pH, so this is also not the right. Flame photometry, this flame photometry is mostly we can use this flame photometry for destruction. If the chemical will be destructed while analyzing it, then we can go for this flame photometry. But if we don't want to destruct that particular chemical, then it is always better to go with GCMS. And this flame photometry is mostly used for sodium, calcium, such kind of magnesium, such kind of chemicals, right? uh, b- uh, uh, and because this is flame photometry, it will give some wavelength, reflectance in the wavelength, and that's how it will be used. Okay. Not destructive, I don't think that this is destructive, but this is based on the this is based on the color and how wavelength it is giving. But GSMS is used for the trace organic pollutant. So this is gas chromatography and mass spectrometry. First, it will separate out the chemicals using gas chromatography, and then it will give the signature in the mass charge ratio, and that's how you can tell, okay, this is that particular compound. You can estimate according to this. So D is the right answer. This is something like this. So this is your gas chromatography, where you can separate your chemical, because we have column. We will talk about this column a little. And then your chemicals will be separated. Then if one chemical will go to this ion source and will ionize it, will change that particular compound into the ions, and one by one ions will go to the mass analyzer, where mass by charge ratio will be calculated, and based on that the detector will detect this mass by charge ratio. And then um, we will have the data system by which we can tell, okay, we have that particular ratio, and that particular ratio is with the is aligning with that particular kind of chemical, right? So this is how we can estimate trace organic pollutant using a GCMS. Which analytical technique is commonly used for heavy metal determination in water? UV visible spectroscopy, atomic absorption spectroscopy, FTIR, GC, that is gas chromatography. If we want to analyze heavy metal determination, yeah, so you have to go with the atomic absorption spectroscopy. Yeah, so this is something like this. If you have analyte, then analyte will go with your some flue gas and oxidizing agent, and you will have some chopper that will chop your analyte. Then there is the atomizer that will create the atom of that particular analyte, and we will have the light source. Based on that light source, atom will give some kind of wavelength, and based on that wavelength, uh, that particular wavelength will be taken up by this monochromatographer, and it will be recorded, it will be amplified, and it will give you uh, some value on the readout device. So this is your AAS. So the thing that you need to take into consideration, that if we have AAS, so then this AAS is uh, mostly AS we use in the metal ion, because we can convert it into free atoms, and this free atom will absorb the light in specific wavelength. If we are talking about a UV visible spectroscopy, then this is best for the colored species and complex, and because it has poor selectivity at trace level. If we have FTIR, this is again one instrument, then it detects the molecular vibration, and so it is useful for organic and non element, for not for elemental metal, because metal do not have that active bonds. Gas chromatography, this is for volatile compound, and because metals are non volatile, so we can't use it for the metal, but it is for the organic compound. Okay, according to the standard practice, MDL, minimum detection limit, is often estimated as mean of blank signal 2 multiplied by sigma of analyte signal, 3 multiplied by sigma of blank measurement, maximum observed noise. So yeah, MDL we can measure using 3 sigma. 3 sigma of your blank measurement. That's why C answer is the right one. If we have precision, precision in sampling and analysis is best evaluated by comparing measured value with regulatory standards, performing replicate measurement and examine their spread, increasing sample volume using a traceable standard. So we have two important terms that we need to take into consideration. One is the precision and another is accuracy. So the precision is can we replicate it? Will it give the same result or not? So precision is more related to replication. Accuracy is if we are comparing it with the measured values, and so is it matching with it or not? So this is accuracy, right? So just keep in mind, precision means can we replicate it or not. So B is the right answer. Now coming to week 4. In gas chromatography, using a non-polar stationary phase, which compound will elute first? Naphthalene, has hexane, phenol, benzoic acid. If we are using non-polar stationary phase, which will elute first? The first thing that we need to consider is non-polar will attract the polar. sorry, non-polar will attract the non-polar. So if it is non-polar, then it will be difficult for that particular compound to go first. It is something that, let's say this is, here you have some chemical, and that chemical is creating the stationary phase, right? And you need to move some chemical over it, right? And if that chemical will be your stationary phase is non-polar. If this will be non-polar, then there will be some interaction with it, right? Non-polar will attract with the non-polar, so every time there will be some interaction, right? So it will take more time to go, is it? Non-polar will take more time to go if the stationary phase is non-polar. So the elute, it will elute at the last, is it? Then we are talking about the boiling. What answer you have given? This is B. Yeah, B is the right one. So, but right now I'm confused with this. Which compound with will elute first? So, if it is a non-polar, then, and if it is also non-polar, then it should not elute first. I'm little. Let me see the explanation for this. Um, if it is a hexane, hexane is the non-polar and has the low boiling point, and the retention time is very short. But if it is a polar, then its retention time will be longer. Okay, maybe my concept was, yeah, you're right. If it is a non-polar stationary phase, and if we will have non-polar, then yes, it will elute first. Yeah, right. My concept got wrong this time. Anyway, so coming to the next question, an analytical method that have the MDL 2 mg per liter, expected concentration of analyte in water is zero point 0.5 mg per liter. What minimum sample volume must be processed so that the analyte mass reaches the MDL? So this is something that, we can just analyze up to, so let's say this is 2 mg per liter, 0.5 mg per liter, 10 mg per liter. So my instrument can only measure my value if my value is aligning between 2 mg per liter to 10 mg per liter, but it can't measure this zero point 0.5 mg per liter. So what I have to do is I have to I have to make some manipulations so that this zero point 0.5 mg per liter can go into this range. So what you will do? What minimum sample value must be processed so that we have the complete? So you gave me 2 by 5, that is equal to 4. Yeah, so you're right. So this is how we have to change our concentration. So volume, sorry, concentration will be same. Okay, now we are coming to the extraction and the concentration, because whenever we have any chemical A, most of the time it is diluted, but for the instrument we need the concentrated. The first thing that we have to do is to extract it into some solvent. So first part is the extraction, and the second part is to concentrate it. right? So we have some method by which we can do such things. uh, so in solid phase extraction, analyte A is first retained by, yeah, if it is a solid, then yeah, we need some sorbent on which it can adsorb. So B answer will be the right one. Yeah, so we do have different step for this solid extraction. So the first is we will do the conditioning. The second is we will add our sample on this solid part, and then we will do the washing, and then we will elute it. Okay, so first part is we have to adsorb our sample on this solid part, right? Sorbent. Okay. The next question is, if we have 1 liter water sample, if 1 liter water sample is extracted into 25 ml organic solvent, the measured concentration in the extract is 2 mg per liter. Assuming 80% recovery, what was the original concentration in water? So this is something that initially we had the volume 1 liter, and now we have just the volume of 25 milliliter, and right now here we have 2 mg per liter of our concentration of, let's say, A, and we have 80% recovery, right? So what was the concentration, original concentration here into 1 liter? Obviously, because we have concentrated it here, then here the density or concentration should be low as comparison to this 2 mg per liter. But how we will do this? So this is a very simple mathematical thing, that if it is a 80% and this yeah, so let me show you. You gave me the answer C, and C1 is the right one. So this is simple. So the measured, what we will do is, first we will calculate the mass. So if we have concentration 0.025, and so we will calculate the mass. So we calculated the mass 0.05 mg, and if 80% is just 80% of the original mass will be 0.05 by divide by point 8, and yeah, so this will give us the value in per liter. Okay. Organic pollutant should preferably be stored in plastic container, glass container, open metal container, paper container. As I told you, organic compound will react with the organic compound, right? Will not react with the inorganic one. So organic compound should be stored in a way that that particular container is not organic in nature. And plastic is the organic, right? Plastic is made up of monomer of carbon. So plastic is not the right option. Then we have glass container. Paper is also organic in nature. Paper will also not be the right answer. Then we have glass container and open metal container. And because most of organic compound may vaporize if it is open, right? Because it has the volatility properties, then open metal concentration container is also not the right option. So the only option now we have is the glass container. If we have inorganic metal ion, then where we can store these kind of inorganic metal ions? Plastic container, glass container, paper bottle, or untreated metal container. Untreated metal container is not the right option. Paper bottle will be wet, and that's how there may be the case of leakage and all. So this is also not the right option. Now we have plastic container and the glass container. Then glass container mostly is organic, sorry, non-organic, so you can say inorganic. So we should not rely on the glass container, but we can put these things into the plastic container, because plastic is organic, and if we are putting inorganic thing in the organic, then there will be no much reaction that we are expecting. Which of the following is an example of sample gain? Evaporation during storage, adsorption onto container walls, carryover from previous injection, biodegradation. So this is something we are talking about error that we will have whenever we are doing the sampling. Whenever we are doing sampling, our sample may increase. Why is that case? So just see. So for example, if in the container you have 5 mg per liter, but if you are transferring into another container 5 mg per liter, let's say, if you are transferring it to another container, it become, let's say, 5 mg per liter. Why is this the case? This will create the error, right? But how the sample can be gained? So let's see the example. Evaporation from storage. If there will be evaporation, then this will give 4 mg per liter, let's say, or 3 mg. It will reduce. So this is your loss, not gain. Absorption onto container wall. So the container wall, if the container wall will absorb, it means it will give, in the next container, it will give less, right? So there will also, we will have the loss condition. Carryover from previous injection, yeah, it may be, or there may be that it already have some concentration, and then we are adding here, and this may give us more concentration. So this is right one. Biodegradation is the loss case. So this is again is not the right option. So C is the right option. Now, most absorption device used in the atmospheric sampling, apart from gas washing bottle, fall into which two main categories? And we have four options here: bubbler and syringe, treated gas absorber and impinger, vacuum tubes and stainless steel canister, syringe and Tedler bag. So this is something that if you have CO2 or O2, and if you need to add it into some liquid, it means you need to absorb it into some container. So we need some particular type of device by which we can absorb it. So what are these device that we can use? So these are mostly fretted glass absorber and impinger. So let me show you the picture of these. So these are impingers that we may have. So yeah, so we can impinge. So we have impinger tube and fret, and here we can also see mid-cat impinger tube and fret. So these are, if we have more fretted glass absorbers, so that will absorb more. So based on this impinger and absorber, we can absorb our gas into liquid, and then we can go with the analytical technique to calculate the concentration of your gas or for a particular contaminant. And now the question is, in ambient air sampling using cold trap, which coolant combination can achieve a temperature of about minus 79 degrees Celsius? And four option that I have is ice and salt, dry ice and acetone, liquid nitrogen, liquid oxygen. So sometime we need coolant so that we have temperature less than minus 70 degrees Celsius to trap our air sampling. So for example, it is CO2 or O2, and we need to trap this gas so that it do not evaporate again into the atmosphere. So what we have to do is we have to reduce the temperature, and so we can use some coolant. Different coolant may have different limit to cool the condition. So if we want to maintain the temperature below minus 79 degrees Celsius, then we can rely on dry ice and the acetone. So let me show you the coolant that we can use. So if we are using the coolant ice water, so temperature that we can attain is 0. If it is ice salt, then we can attain the temperature of minus 21. If the coolant is dry ice and acetone, then temperature that we can attain is minus 79 degree. So to maintain the temperature, to trap the air sampling into some liquid, you need some coolant, and that coolant, this minus 79 temperature that we can attain using the coolant, that is dry ice and acetone. Now moving to the week 5, which indicator is used in COD titration? As I told you, for the COD, that is chemical oxygen demand, we are using strong oxidizing agent, right? And we will add that strong oxidizing agent. But how much we have added? We need some indicator for that. So which indicator we will use for this COD titration? So to calculate COD, we need Ferroin indicator, and that Ferroin indicator will change the color from blue green to reddish brown, and that's how we can tell how much dichromate. Dichromate is your strong oxidizing agent that we are using. So how much dichromate we are using. So this will give us the value, and that's how it will give us the COD value. We have bioassay. So bioassay is primarily used to, we have four options: measure total carbon, assess biological toxicity, measure oxygen demand, identify biochemical structure. So because bio is related to the biological toxicity, so a B answer will be the right one. And this is something like, if for example, if we have mercury, it may be that 0.01 mg per liter of mercury may be hazardous for us. But if we are consuming, let's say, ozone, tropospheric ozone, or PAN, one of the photochemical compound, and even so, if let's say we are taking 4 mg per liter, so effect, let's say, may be the same. So bioassay is assessing the biological toxicity. So at particular, what threshold we should put for each of these chemicals, right? We can't put the same threshold. So bioassay will measure this biological toxicity to specific chemicals. Okay, because we were talking about the sampling, and to concentrate it and first to extract and then to concentrate it, right? So uh, we have one filtration. So if we are filtering our sample, so there may be pressure drop that may increase during filtration. But why is this the case? Water density changes, filter became clogged with solid, vacuum pump weakens, pore size increases. So for example, if we have benzene, let's say in the soil, and if we want to extract it into some solvent, so what we have to do is we have to do the filtration so that our soil can be removed, right? So pressure drop may increase. So yeah, pressure drop may increase because the filter uh, may become clogged with the solid, and that's how pressure drop will increase, and that will make difficult for us to extract our solvents, extract our chemical of interest into the solvent. Okay, because we talked about the extraction process, but after extraction we also have the concentration process. So for concentration we do have different technique, and one of the technique is rotary evaporation. So rotary evaporation reduce the boiling point mainly by increasing pressure, applying vacuum, adding nitrogen, cooling the flask. So this is something that after extraction we have the concentration 10 mg per liter, but we need the concentration just 2 mg per liter. So we can evaporate the solvent. But how we will evaporate the solvent? We can boil it, right? We can boil it. But with the boil we have some challenge, and that challenge is, our if we have this chemical A, if this chemical A is in organic and it may also have the tendency to evaporate, then this may also evaporate, right? So what thing that we need to consider is to reduce the boiling point, to reduce the boiling point. So how we can reduce this? This is, we can apply the vacuum. So if we are applying the vacuum, so vacuum is taking more solvent. The boiling, we are boiling it less, so we can have our chemical here only, but our solvent may evaporate after applying vacuum and giving some temperature. So this is rotary evaporator is like this. Okay, the flask, we rotate the flask in rotavapor. Why? Increase pressure, increase surface area, and prevent bumping. Cool solvent, separate analyte. So we increase the surface area so that there is the more evaporation, and we also prevent the bumping. uh, that's why we just rotate it. Okay, the another technique is the nitrogen blow down. So we can flush the nitrogen into our solvent that have the chemical species A, and this blow down will blow the nitrogen. Your solvent will be replaced by the nitrogen. So your solvent will be vaporized, or will go out, because nitrogen will replace it. So nitrogen blowdown work by oxidizing solvent, increasing solvent vapor pressure gradient, increasing pressure in vial, cooling sample. So yeah, so what we are doing is we are adding that nitrogen again and again. So what we are doing is we are increasing the solvent vapor pressure gradient, and that's how the solvent can go up. So this is something like that. Another way is the Soxhlet extraction. So Soxhlet extraction is done by single solvent washing, continuous reflux and chiffoning, vacuum filtration, centrifugation. So if we want to extract the chemical, so we have one technique, that is Soxhlet extraction. So how does it work? So it work with continuous reflux and chiffoning. This is very tedious and the long time taking process. So for example, so here you can see, so this is continuous solvent extraction method that we can use to extract, for example, pesticide lipid from solid sample. It is very difficult to extract from the solid sample, right? It is very exhaustive process. So that's how we do have the chiffon tube, and then we have condenser. So repetitively we are repeatedly we are we are giving the temperature, then there is the condenser, then that one is going that side. So we are repeating the process till all the extraction is done. So this is very exhaustive one. Ultrasonic extraction we can also done, and here the principle is the cavitation bubbles. I have a lot of MCQs, but I think this is what I was able to cover. But yeah, today only I will upload all the slides by tonight only, so you can see, and that's how the course is completed. Little bit revision I tried to I tried to make it completed, but anyhow it couldn't. But yeah, all the best for your exam, and if you need my help, just mail me anytime. I will try to give you response as soon as possible. And yeah, happy reading. This is the time that you can go for your dinner, and yeah, best of luck. Thank you, Lakshmi.